Oops. Hello, chemistry students. We're going to talk today about isotopes. Now, before we get started, you should get your chem helper. And if you don't have a chem helper yet, you can always bring up the one that I have posted to our homepage. All you have to do is go there and click on the picture that says Chemistry is for Winners, and it'll pop right up. You may want a calculator, so you can use your phone or a real calculator. And you'll also want to pull up the Isotopes Guided Notes worksheet that I uploaded to a CamiDoc and linked to our agenda. So if you need to pause the video now to get ready, then go ahead and do that. Okay, we're going to kick this discussion off by defining isotopes first. Isotopes are atoms of the same element that have different amounts of neutrons. So isotopes are atoms of the same element that have different amounts of neutrons. So let me just give you an example of what this even means. First of all, atoms of the same element are not always the same. So if you have a gold nugget, like a big chunk of gold that you're holding in your hand, all of the atoms that make up that gold nugget may not be the same. They might be a little bit different. Are they still gold? Yes. But they may have different nuclei. They may have different numbers of neutrons, which means that they are isotopes of each other. So the neutrons, the number of neutrons, is what's going to make one gold atom different from another gold atom. It's never a different number of protons. The protons that are found in an atom are kind of like a fingerprint for that element. So all atoms of gold have 79 protons, and all atoms of fluorine have 9 protons. If you change the number of protons in a nucleus, you have changed the identity of the atom. If you look at the periodic table, no two elements have the same atomic number. The atomic number defines the element. If you change the protons, then you have completely changed the element. But if you change the neutrons, you haven't changed the element. You've just changed the mass of the atom. And you haven't changed the charge of the atom by taking away or adding neutrons, because neutrons have no charge. So all that we're doing when we're talking about isotopes is we're looking at the size of the nucleus and the mass of atoms that have that number of neutrons in it. Let's take a look at some other examples. Now you've got this picture on your note sheet, so let's go over some of our particulars here. First, let's look at hydrogen. Hydrogen is the very first element on the periodic table. All atoms of hydrogen have only one proton. You cannot call an atom hydrogen unless it has one and only one proton. If it's got more than one proton, it's not hydrogen anymore. So let's take a look at the 3 different forms of hydrogen that we have. In hydrogen 1, we have 1 proton. In hydrogen 2, we have 1 proton, but guess what? We have another particle in the nucleus shown by this green circle with a 0 in it. That is 1 neutron. So hydrogen 2 has two particles in the nucleus. One of them has to be a proton because it's hydrogen. All hydrogen atoms have 1 proton in it. And then the other one must be a neutron. In hydrogen 3, once again, we have 1 proton. And since our mass number is 3, and the mass number tells us how many particles there are in the nucleus, the other 2 particles must be neutrons. So hydrogen 3 has 3 particles, 1 proton, 2 neutrons. Hydrogen 2 has 2 particles, 1 proton because it's hydrogen and it has to have 1 proton, and 1 neutron. Hydrogen-1 has 1 particle in it, and that particle has to be a proton because all hydrogen atoms must have a proton. Okay, let's take a look at our helium atoms. Helium has an atomic number of 2, which means that all helium atoms must have 2 protons in order to be called helium. Anything different, and it's not helium. So helium-3 has 3 particles in the nucleus. 2 of those particles must be protons because that's the atomic number of helium. The third one is a neutron. In helium-4, we have 4 particles in the nucleus. 2 of them must be the protons because it's helium, and then the other 2 must be the neutrons. All right, lastly, let's look at lithium. 2 forms of lithium. All lithium has 3 protons, and I know that because that's the atomic number for lithium. In lithium-6, I have 6 nuclear particles. I know 3 of them must be protons, and so the other 3 must be neutrons. And then I have helium-7. In helium-7, I have the requisite 3 protons, which means that the other 4 particles must be neutrons. And so once again, just to kind of hit this home, our mass number is simply a count, a quantity. It's telling us how many particles there are in the nucleus. And since we always know how many protons we have, just by subtracting protons from the mass number, we get the number of neutrons. Okay, so let's practice that. So you have a data table that I put on your note sheet, and in the corner, in the very first column, you're going to have to write down the isotope abbreviations. So for your first column, you should write this isotope abbreviation. What we're talking about here is uranium-237, and I want to change my pen color here so you can see better. There we go. So we're talking about uranium-237, and I put a picture of uranium up there. It's kind of like a very insignificant looking rock, but it is used in nuclear reactors and to make nuclear weapons. Okay, back to our math here. So this is our first isotope. The atomic number is the number of protons, and that's always the bottom number in this notation. So we have 92. And as I said, the atomic number is the number of protons, so that also is 92. The number of electrons has to equal the number of protons. Why? Because atoms are neutral, and so they have to have equal numbers of positive things, protons, and negative things, electrons, so that they can cancel each other out and retain a neutral charge. The number of neutrons is simply these 2 numbers subtracted from each other. So when I punch into my calculator 237 minus 92, I get 145. That's how many neutrons I have in the nucleus. So the total number of nuclear particles is 237. 92 of those are protons. 145 of them are neutrons. Okay, let's try and do the next one on your own. Go ahead and do that. I'm going to pause it, and then I'll show you the answer. All right, you can go ahead and check your answer. Hopefully you got it right. Now, what's the difference between uranium-237 and uranium-238? Well, the difference is right here. It's the number of neutrons. The number of protons are the same. So since the number of neutrons are different, uranium-237 and uranium-238 are isotopes of each other because they have a different number of neutrons, and yet they're atoms of the same element. How do I know they're the same element? Because they have the same atomic number. Let's try another example. So please go ahead and put cobalt-48 in your data table. And while you're at it, you may as well put in cobalt-60. I'm going to go ahead and pause this, and I want you to figure out what's the atomic number. What's the number of protons, the number of electrons, and the number of neutrons? Let's see if you remember this from our parts of the atom activity. Okay, here are your answers for that first row. I wanted to just go over how I got these answers so that you could try the next one on your own. So, our atomic number is not listed in this notation. So remember, here we have the name of our element, which is cobalt, we have a dash, and then we have the number 48. The number 48 here is our mass number. How do we find the atomic number? We have to find cobalt on the periodic table. Our atomic number for cobalt is 27, which means that that's how many protons we have. And the electrons have to equal the protons. So our first three numbers here are 27. How do we find the number of neutrons? In your calculator, punch in 48 minus 27, and you get our number of neutrons, which is 21. Okay, try the next row on your own. And here's your answer for the last row. Okay, let's move on. We have a little bit more practice to do here. Pick a different color. All right, go ahead and add in these 4 isotopes for lead into your data table. And go ahead and figure out how many of each nuclear particle we've got. So you're just doing the very same thing that we did before. I'm going to pause it, do it on your own, and then hit play again. All right, hi there. So in this table, I've got atomic number, protons, neutrons, and electrons, but I'm pretty sure that on your sheet, you've got electrons, like electrons and neutrons are switched on yours. So when you're checking your answers, just make sure that you're looking at the correct column there. So the only one that does not have the number 82 in it is our column of neutrons. So remember, all of these different forms of lead, they're still lead. The only difference is that some of them have more neutrons than the other. And so our isotope with the smallest mass, lead-204, has only 122 neutrons. It's still like a large atom. Lead-206 has 124 neutrons. Lead-207 has 125. And lead-208 has 126. So again, make sure that you're looking at the right column when you are checking those answers. Okay, I want to put this on pause because there's a pie chart that I want to show you, and I need to switch screens. Okay, hi, thanks for waiting for that moment. So I wanted to show you this pie chart because this is going to lead into something that we're going to talk about next week. And that is a calculation that's called average atomic mass. Now, I'm not going to ask you to know how to calculate average atomic mass, but I do want you to understand how that value is reached by scientists. And so the point is this. So we've got the 4 different forms of lead. For instance, that I just had you calculate and that I just showed you the answers for on the note sheet. Even though we have 4 forms of lead, they don't all occur as much as the other one. What I'm trying to say is that one form of lead is more rare, and there's another form that is quite common. So they don't all exist in the same amounts in the universe, in nature. So if we take a look at this pie chart that I've got on the bottom of your form, you can see that there is one form of lead that really stands out as being the most common. And that form is the one that we have in red, which is right here. And red corresponds to lead-208. So the one that actually is the heaviest is the type of lead that is found most often in our universe. And so that's what I wanted to end with you today, is just so that you know that even though hydrogen has 3 different forms, and lithium has 2 different forms, and lead has 4 different forms, they're not found in equal amounts in our world. They can be found in differing amounts. And that's the last thought that I want to leave you with. Thank you very much for watching, and I will see you in class. Bye-bye.